Suppose you wanted to find what root 4.08 was. Mathematically, this is literally as far as you're going to get. Analytically, you're just going to say 4.08 to the... However, if you need to find, say, a decimal approximation for physics or chemistry, you're going to need to do something called differential approximation, where you use derivatives to approximate. Let us go back to derivatives. Say, here's how we write them. dy dx, say, equals 3. dy and dx are basically infinitesimally small changes in each variable. This is an infinitesimally small change in y, which is practically 0. This is an infinitesimally small change in x, that is practically 0. Even though both are pretty much 0, there is still a ratio. For every extremely small change in x, there are 3 of those extremely small changes in y. We can also say that dy dx might as well be delta y delta x. These are equivalent. This is change of y, change of x, but this only deals with incredibly small values. This could deal with more realistic values. Like we'll see here, delta x will be 0.08. Now, what we do here is that we make a function that we can use to help find this. Let's say y equals root x. Already you can see a resemblance. If you can't, go to science. Okay, let us graph this. At x equals 4, y equals 2. It's this little point here. But we want to find root of 4.08. So it's, when x is 4.08, which is about there, and the curve continues, and it's about here. We want to find what that y value is. We can say that delta x is the x value that we want to get, x want, minus x have. The x value we have is the most practical one, x equals 4 and y equals 2. Delta x, therefore, is 4.08 minus 4, which is just 0.08. Now the y value we want is the y value we have, this is 2, plus delta y. We're going to find delta y. Okay, now let us find dy dx at this point. It's very simple. Root x derives into 1 over 2 times 1 over root x. We plug in 4, and we get 1 over 4. So delta y over delta x is 1 over 4. What is delta x? Let's go back here. Delta x is 0.08. So then we say delta y is 1 over 4 times 0.08. This is just 0.02. Delta y is 0.02. Assuming this function here was just a line, it would go up by 0.02 units. Now let us plug it back into here. Y value we want, y want, is just 2 plus 0.02, simple addition, 2.02. Then we say root 4.08 is approximately 2.02. That is differential approximation. Let's give you an example. You can do something else, and I'll try and walk you through it. Let me attempt to erase this. What is e to the 0.03? Honestly, we cannot figure this out without either the scientific calculator or differential approximation. Let's do that. So we have a function y equals e to the x. I'm going to go through this very quickly. We have this point here that's very familiar. When x is 0, y is 1. We want to find the value of this function when x is 0.03. So let's find delta x. Delta x in this case is 0.03 minus 0, which you should know is just 0.03. Now we need to find dy dx. dy dx is, in this case, just e to the 0. We're going to find dy dx at the point we know of. And in this case, this is just 1. So delta y over 0.03 equals 1. Delta y is 0.03. The original y value is 1. We add the change in y, and we get 1.03. 1.03 is approximately e to 0.03. Suppose you wanted to know, say if it was a question on the AP, whether when we approximate it was an overestimation or an underestimation. Assuming the point we have is always to the left of the point we want to get, and if it's the other way around, you just reverse everything I said. if a function, say, is concave up, and we wanted to figure out what this was, and we had this point, we're going to use this dy dx, this tangent, and you'll notice that since the derivative is always increasing, if this is where we think the point is, it's always a bit lower than here, where it actually is. Going left to right, you will always underestimate on a curve that's concave up. Conversely, say this is the point we have and this is the point we want to get. If we use this derivative, since it's concave down and the derivative continuously decreases, going left to right, we always overestimate on a concave down function. This is where we imagine it to be. And that is about it. Yeah. Hold on a second.